Now that we have covered the core fundamentals of data warehousing, it's time to level up things a bit and explore the different architectural approaches that you can use when designing a data warehouse system. We will begin with the most common and straightforward model, that is the centralized data warehouse. In this setup, all your data lives in one central database and that powers the reporting, business intelligence, and analytics. After that, we'll move into data marts, which are basically smaller and more focused versions of a data warehouse. They are designed for specific teams or business functions. We'll compare data warehouses and data marts side by side because that becomes really important when we shift into component based architecture. Unlike the centralized approach, a component based data warehouse environment is made up of multiple pieces working together. Things like data warehouses and data marts combined into a larger ecosystem. The key idea here is that you're building an environment, not just one giant database. We'll walk through several architectural options, including a quick introduction to specialized databases called cubes, which are often used to speed up analytical processing. We'll also discuss something called as operational data store or ODS, which is a variation of data warehouse that can be useful in certain architectural scenarios. And finally, we'll look under the hood of a data warehouse and explore the staging layer, the area where data first lands before it gets cleaned, transformed, and integrated for reporting and analytics. And with that, let us get into the world of data warehousing architecture. When we talk about different data warehousing architecture, let us start with the simplest one, that is the centralized data warehouse. Just like the name suggests, everything lives in one single data warehousing environment instead of being split across multiple systems or component. In an ideal world, this is usually the default architecture that you'd want to go with, but on paper, this sounds super straightforward. Now, if you ever worked with people who have been around since the early days of data warehousing, they will probably tell you that the centralized warehouses looked easy in theory but were often difficult to handle in practice. In centralized setup, all your source systems feed data into one database. Reporting, dashboards, business intelligence, analytics, everything pulls data from that one place. It is basically a one-stop shop for data, almost like a giant data supermarket. And honestly, it's a very clean architecture to draw, but historically, building centralized warehouses was not nearly as simple as this diagram made it look. If you remind back to the earlier generations of data warehousing, the technology itself was still evolving. Relational databases, which today are the backbone of most data systems, were still relatively new at the time. The whole data, the whole idea of organizing data into rows and columns was easy enough to understand, but the actual database products were immature and struggled badly with massive data volumes. On top of that, the industry was still figuring things out through trial and error. There was not a huge body of knowledge around data warehousing yet. So naturally a lot of architectural engineering and data modeling mistakes were made along the way. And then there was human side of the problem as well. A centralized data warehouse requires a lot of cooperation across departments and teams. Different business units have to agree on definitions, standards, ownerships and processes, and as you can imagine, getting that level of organizational alignment is often harder than the technology itself. Honestly, that challenge still exists even today. The good news, however, is that things have improved massively over time. The technology has matured, database systems are far more capable, and we now have decades of experience and best practices to learn from. Building centralized environments today is far more practical than it used to be. You can even think of modern data lakes as kind of evolution of the centralized warehouse idea. Underneath, they may be slightly, or should I say, highly distributed because of big data technologies, but from users' perspective, they still feel centralized, one place where all the data is available for analytics and decision making. So, that original vision of one stop shopping for enterprise data is actually becoming much more achievable as modern platforms continue to evolve. Chances are you are probably obviously have heard of the term data mart, and you're probably wondering how it is different from a data warehouse and where the two kind of overlap. Remember, when we talked about a data warehouse is not always the final stop for data coming from the source systems into an analytics environment. In many setups, the data keeps moving downstream into smaller, more focused environments called as data marts. Think back to this analogy. Source system here, they are like data supplier. Data warehouse, they are like the wholesaler, and data marts, they are like the retail store. Now let us zoom in into this retail stores for a bit and understand what this data marts actually are. In this example, the three data marts are pulling their data from the central data warehouse. These are called as dependent data marts because they rely completely on the data warehouse to exist. No warehouse means no data mart, since that is where they get their data from. There's another type called as independent data mart. Unlike dependent ones, independent data marts don't need a data warehouse at all. Instead, they pull data directly from one or more source applications. And we'll get into facts and dimensions later on. But for now, you can think of an independent data mart as basically a small scale data warehouse focused on a specific business area. With dependent data marts, data comes from the warehouse. There is usually better consistency across different marts, and the architecture tends to overlook, or should I say, architecture tends to look cleaner and more organized. You typically get a neat left to right flow of data from source systems to warehouse to marts and then the end user. With independent data mart, things obviously can get messy very quickly. Since each mart pulls data directly from the applications, there is often very little standardization. For example, concepts like customers, products, or employees might be represented differently in every single mart. And if an organization has dozens of independent data marts, the architecture can start looking like spaghetti. Lots of overlapping data pipelines feeding data again and again into different marts from the same system. At this point, you might wonder what is really the difference between a data warehouse and an independent data mart. And honestly, the line is pretty blurry. A modern data warehouse usually connects to many data sources, maybe dozens or even hundreds. It uses ETL processes to bring all that data together into one centralized environment with massive data volumes. An independent data mart works in a very similar way, except it usually deals with fewer data sources, maybe just 1 to 5 systems instead of dozens. Other than scale, the concepts are surprisingly similar. So, in many real world cases, the difference between a data warehouse and an independent data mart is more about perspective and scope than some strict technical rule. So far, we have only talked about the idea of having one centralized data warehouse as the main default approach, but we have also introduced data marts, which takes us into a more component based style of data warehousing. In other words, instead of one single centralized environment, you now have multiple connected pieces working together. And honestly, this is where choosing a data warehouse architecture starts becoming a lot more interesting and a lot more complicated. It's no longer just one big warehouse versus no warehouse. There are multiple ways to structure the environment depending on the organization's need, technology, and even internal politics. However, the diagram that I'm showing you here shows all the major approaches all at once. But obviously, rather than trying to observe everything together, let us break down step by step. The first decision obviously is simple. Do we want a centralized environment or do we want a component based environment made up of multiple pieces? Now, if you go with a centralized approach, there are some very strong advantages. And honestly, if possible, this should be your default choice. A centralized warehouse gives you that single source of truth that data warehousing was originally built for. Everything lives in one place, which makes reporting, analytics, and governance much more cleaner and easier. Modern technology also makes a centralized system much more practical compared to the early days of data warehousing, because scalability and storage and processing powers are all significantly better now. However, there's obviously a catch. A centralized warehouse requires a high level of cooperation across the organization, just like how I talked about earlier. Different teams have to agree on definitions, business rules, governance standards, and how data should be managed. And as you can imagine, that is always not an easy. Uh, Another challenge is that changes in one area can ripple through the entire system. That adds a new application, or modifying a source system, and suddenly multiple downstream processes can get affected because of that. On the other hand, however, we also have component based approach. Here, instead of building one giant environment, we divide the system into smaller pieces or components. This approach has real benefits too. For example, changes in one component does not necessarily affect everything else. Different teams can also use different technologies if needed. Maybe one group uses a newer database platform while another uses a different BI tool. So you get flexibility and a kind of a mix and match architecture. If done properly, these components can still integrate with each other and work together as a larger ecosystem. Although in practice, that integration is usually harder than it sounds on paper. Component based systems can also help organizations deal with political or operational challenges by using a divide and conquer strategy. But again, there are trade offs. One of the biggest issue is inconsistency. Different component may define or calculate things differently, which can lead to conflicting reports and analytics. Integrating those separate components can also become difficult over time. Now, within centralized environment, there are many paths that we can take. The classic option that we have is EDW, that is Enterprise Data Warehouse. This is basically the traditional model where we build one centralized warehouse to support analytics across most or all of the organization. You'll also hear people talk about data lakes, which are sometimes considered a newer generation of centralized data platform. Instead of relying purely on relational databases, organization use technologies like cloud storage systems like AWS S3 or Azure Data Lake or other large scale storage environment to build out data lakes. And even within EDWs, there are technology choices. Some organizations use traditional relational databases, while others use specialized large scale analytical databases or data warehousing applications designed specifically for heavy analytics workload. Now, let us switch to the component based architecture. Once we choose the component route, we generally have two styles, that is architected and non-architected approaches. In architected approach or architected environment, components are designed to work together intentionally. One option is combining a central warehouse with dependent data marts. Think of this almost like a supply chain. The warehouse feeds the mart. A well-known variation of this idea is Corporate Information Factory or CIF. Now, CIF is not as common today, but you'll still hear about it in the data warehousing discussions. Another variation is the front end data mart approach. Here, the data mart sits in front of data warehouse rather than behind it. For example, separate business units might each have their own analytics focused data marts, and then selected data from those marts eventually flow into the larger data warehouse. Then we have another important architected model called as data warehouse bus architecture, that is DW bus here. This model is based heavily on the idea of conformed dimensions. That basically means all the data marts should agree on common business entities like customers and products and employees and geography and so on. So even with a different even if the different marts are built differently or use different technologies, they still maintain consistency around core business concepts. In theory, again, it sounds great, but in practice, achieving true conformed dimensions across an organization is extremely difficult because the challenge is usually organizational rather than technical. And finally, we come to this federated EDW, or federated data warehouse. This is basically the agree to disagree model. Different teams build a independent data marts with their own business rules, structures, and definition, and then collectively label them as part of a broader warehouse environment. The downside, obviously, is that different systems may give different answers to the exact same question. Historically, however, this became popular in late 1990s when many early data warehousing projects struggled. Organizations often settled for smaller, isolated solutions because partial success was considered better than no solution at all. Today, however, with modern platforms, better technologies, better databases and data lakes, and much stronger industry knowledge, federated approach are usually considered a last resort rather than a preferred design. You generally don't want dozens of disconnected data marts spread across organization if you can avoid it, and that is really the biggest takeaway here. There's no single architecture that works perfectly for everyone. Data warehousing is part science, part architecture, part art, and part organizational strategy and management. We do have some general guidance like preferring the centralized approaches when possible, but ultimately the best solution depends heavily on the realities of the organization, its team, and its business goal. Okay, now when we talk about data warehousing, it's important to understand where cubes fit into the picture. So far, we have mostly seen how relational database management systems are the standard foundation for the data warehouses and data marts. But for many years, cubes were also very popular alternative. Before I start talking about cubes, I want to clarify something very important. You might hear people say that cubes are an outdated technology, and to some extent that is partially true in terms of how modern BI systems are evolving. Traditional OLAP cubes, especially older multidimensional cube implementation, are not as dominant today as they were like 10 or 15 years ago. Modern platforms like Microsoft Power BI and Tableau and cloud warehouses and lake houses architecture, then they can now perform analytics much faster directly on the modern storage engines. So many organizations no longer rely heavily on this classical cube architecture, but that does not mean cubes are irrelevant. In fact, the concepts behind cubes are still extremely important because modern BI tools still work on the same analytical thinking. Dimensions, measures, aggregations and hierarchies and slicing and dicing and drill downs, all of these ideas come from OLAP and cube based analytics. So even if you have never built a traditional cube in your future job, understanding cubes helps you understand how analytical systems think internally. Think of it like this: we may no longer manually drive old cars without power steering, but learning how engines work still matters. Also, many enterprises still run legacy BI ecosystem where cubes are actively used in production, especially in fields like banking and telecoms and manufacturing and insurance and large enterprise reporting systems. And so in this particular section, what I'm going to do here, just don't I'm trying not to treat cubes as an old technology. I'm going to treat them as a foundation for understanding modern business intelligence and analytical modeling. Before moving ahead, however, to understand what a cube is, I want to talk about what it is not. A cube is not a relational database. Instead, it is a specialized type of database designed specifically around the concept of dimensions. In other words, it naturally understands data in terms of things like time and locations and product categories and cell region and so on. In the early days of data warehousing, cubes were actually one of the leading technologies in this space. Tools like Express and PowerPlay were widely used, and many of them were built around the multi-dimensional databases rather than the traditional relational systems. Even today, cubes are still used, although mostly for smaller scale data warehouses and data marts instead of massive enterprise-wide system. One major advantage of Cube obviously is speed. They can deliver extremely fast queries and reporting performance because the data is already organized in a way that makes analysis efficient. They work especially well when the data volume is relatively low or moderate and the structure of the data is not changing very often. Years ago, like even 100 GB of the data was considered huge for a data warehouse. Today that is obviously very small compared to the scale of modern enterprise data environment that we have nowadays. Now cubes are obviously fast, but they come with some trade-offs. Obviously, compared to relational databases, cubes are much less flexible. The structure is fairly rigid because they are optimized for high performance reporting. Once that structure is set up, making changes later can become much more difficult. Another thing that you should notice here in cube technologies is that they vary often. They vary significantly from vendor to vendor, much more than the traditional relational databases do. Because of this, many modern organizations they use kind of hybrid approach that is also outdated, but they combine relational databases and cubes together within the same data warehousing ecosystem. For example, imagine a central data warehouse running on a relational database platform like SQL Server. That data warehouse might then feed the data into several downstream data marts, some of which are built using cubes for faster analytical reporting. You might even see a mixed architecture where one data mart uses a relational database while other use multi-dimensional databases depending on the business need. From the end user's perspective, however, we usually try to hide all this architectural complexity. Users typically don't interact directly with the SQL tables and cube architectures or backend storage systems. Instead, they access the data through BI and visualization tools like Tableau and Microsoft Power BI, which provide a cleaner and user-friendly analytical interface regardless of the underlying technology. So overall, cubes and relational databases they are not necessarily competitors. In many organizations, they actually complement each other, creating a powerful data warehousing environment. Now, let us broaden our view of data warehousing and talk about operational data store or ODS. Here we have typical data warehouse setup and alongside it a typical ODS setup. So what is a ODS exactly? Just like in data warehouse, an ODS brings together data from multiple source system into one centralized place. The difference, however, is in the kind of data that it focuses on. A data warehouse is mainly designed for historical analysis, while an ODS is focused mostly, sometimes entirely, on current operational data. In many cases, data flows into an ODS in real time. For example, if a transaction happens at a point of sale system, that information can be pushed immediately into the ODS instead of waiting for the next scheduled ETL batch process like we usually see in traditional data warehouses. And that is an important distinction. One of the classic characteristics of a data warehouse is that it's time variant, meaning it stores historical snapshots of data over time. I'll dive deeper into ETL models later on, but for now, just remember that ODS is much more about the present moment. If you think back to the different types of business intelligence question that we discussed earlier, and ODS is basically answering the question that is what is happening right now. It is not primarily concerned about the historical trends or future prediction through predictive analytics. Instead, it is focusing on the current state of operations by combining the live data from different systems. So ODS environment became especially popular in late 1990s and early 2000s during what many consider the second generation of data warehousing. Organizations were building basically large scale data warehouses for strategic decision making, while ODS platform handled operational decision making separately. Back then, and even today, in some cases, there were two main approaches. One was to feed the data separately in both ODS and the data warehouse in parallel. Users would then choose which system to use depending on whether they need operational insights or strategic analysis. The second approach was the sequential load, that is to load or first load the data into ODS and then pass it downstream into the data warehouse. In this setup, the ODS also act kind of like a staging layer. The user experience stayed almost the same. The main difference, however, was how the data flowed behind the scene. Traditionally, ODS system, they are not as common as this as they once were. One major reason is that the modern data warehouses are much more faster and support far lower latency than the older system did. The gap between the operational and analytical environment has also become much more smaller. Another reason is obviously the rise of big data technology, something that is not suited for the ODS. Remember the three V's of big data? One of them is the velocity. Modern big data platforms can ingest and process data almost in real time that allows organizations to perform operational analytics directly on those platforms instead of maintaining a separate ODS. In some modern architecture, you may still find an ODS like a component inside a larger data lake ecosystem working alongside more strategic analytical platform. That said, however, ODS systems definitely have not disappeared. Many legacy ODS platforms are still running today, and organizations continue building new ones for mission critical operational use cases where real time visibility is essential. So basically, if we revisit the bigger picture that I have been building throughout this slide here, is we now have data warehouses, the data lakes, the data virtualization, and the ODS environment all working together alongside the business intelligence tools. Depending on the needs of the organization, different combinations of these technologies can support modern data driven decision making and operational action. Nevertheless, when we talked about operational data stores, we saw that one common architecture pattern is to place an ODS in front of the data warehouse as a staging area. But honestly, even if your organization does not use an ODS at all, every data warehouse setup still needs some kind of staging layer. So, if we open up a typical data warehouse architecture, you will usually find two major layers sitting side by side, that is the staging layer and the user access layer. I'll talk about the user access layer shortly, but you can think of staging layer as the landing zone for the incoming data from source system. Remember, a data warehouse does not generate data itself during day-to-day business operation. The data is coming from other applications or databases or systems. That is why the staging layer becomes such an important part of E in ETL, where E stands for extract. The main goal here is to pull data from source systems as quickly and efficiently as possible, especially when those systems are handling massive transaction volumes and are already heavily optimized for operational work. We don't want them to slow down, we just want them to quietly grab the data we need with minimal disruption. Once the data reaches the staging layer, then we can start doing the heavy lifting like integration and cleaning and transformation and formatting and whatever the other processing is required before the data is ready for the analytics and reporting. There are actually a couple of different ways staging layer can be designed, and we'll look at those shortly. But before that, I'll want to quickly understand the role of the user access layer. Well, this is basically the part users interact with directly. From a business user's perspective, this is the data warehouse or the data mart they actually see and understand. Everything related to dimensional modeling, star schemas and snowflake schemas and fact tables and dimension tables and so on exist inside this layer. This is where the reports and dashboards and BI tools and analytics query actually operate. So if I just zoom back out here and look at different workflow, data does not move directly from source system into reporting dashboard. There is an important stop in between. First, the data lands in the staging layer, gets processed and transformed, and then moves into the user access layer in a business friendly format. Now let us zoom in into the staging layer itself. Imagine that you're working with a university system, and this is a very common example that exists over here. To keep things simple, let us say that we only care about two subject areas, that is departments and faculty member, and for simplicity assume each subject is stored in just one table, even though in real world system there would usually be multiple related tables. Inside the staging layer, what often we do is create near mirror copies of the source structure. Why? Because our goal is fast and non-intrusive extraction. The closer the staging tables resembles the source table, the easier and smoother the data movement becomes. Now let us make this example a little bit more realistic. Suppose the university has multiple campuses, say East Campus and West Campus, and each campus manages its own faculty system separately. Maybe both campuses use the same software, or maybe they use completely different systems. In this staging layer, we would typically create a separate staging tables for each campus. So we would have East Campus faculty table, each East Campus department tables, and equivalent tables for the West Campus as well. Later, during transformation and integration, we combine all of those tables into unified university-wide data inside the warehouse. At that point, users can still analyze the data campus wise if needed, but the data warehouse itself presents a consolidated view. Now you might wonder, why not merge everything directly into the staging layer itself? Well, you can do that if the systems are perfectly aligned. For example, if both the campus use identical software with the same structure and standards, then combining feeds early may work fine. But in many real world situations, obviously alignment differs, systems differ. Maybe the software versions are different. Maybe one campus customizes its application, or maybe entirely different vendors are involved. In those cases, keeping one-to-one feeds into staging is usually the safer and cleaner approach, and that is an important mindset shift. The staging layer is not the final business ready warehouse. Users never really interact with it directly. It is just a temporary holding and processing area for raw incoming data. So the key objective of the staging layer is to focus primarily on extraction, not transformation. We want to move data out of the operational systems quickly and then handle all the complex processing safely inside the data warehousing environment itself. Now, I briefly mentioned earlier that there are two different kinds of staging layer that you can use in a data warehouse. So let us properly understand what they are and how they differ. Remember, when you look inside a data warehousing, even in a centralized setup, there are multiple layers working together behind the scene. One of the most important is the staging layer, which basically acts as a temporary landing zone for incoming data. Data first arrives here from the source system, gets cleaned, transformed, and integrated, and then finally moves into the user access layer where reports and analytics happen. Now, the staging layer usually stores data in a format that looks very similar to the original source system, and based on how we manage this stage data, we generally have two approaches, that is non-persistent staging layer and persistent staging layer. Let us talk about the first one, that is the non-persistent staging layer, because it is easier to visualize. So with a non-persistent staging layer, the staging area is emptied after every load cycle. Before fresh data comes in, the staging layer is basically blank. For example, imagine a university is onboarding 4 new faculty members at the beginning of a semester. The information comes from a faculty management system into the staging layer first. Once the data is validated and processed, it gets loaded into the user access layer where it is added to the existing faculty record. Now, here's the important part. Once everything has been successfully loaded into the user layer, the staging layer is cleared out completely. That is why it is called as non-persistent. The data does not stay here permanently. So the next time the two more faculty members join, the process starts again with an empty staging layer. Their data comes in, gets staged, moves into the user layer, and then staging layer is wiped clean once again. So that is basically the workflow. That is, the data comes in, gets staged, moves to the moves to the user layer, and staging area gets emptied. But let us compare that with the persistent staging layer. In a persistent staging layer, the data is not deleted after processing. It stays there even after it has been loaded into the user access layer. So let us say the same four faculty member arrived during the first semester. Their data moves into the staging layer and then into the user access layer just like before. But this time, after the process is complete, we do not clear the staging layer. Later, when these two new faculty members join in the next semester, the staging layer already contains the earlier faculty data. We simply add the records on top of the existing ones, move the required data into the user access layer, and still keep everything stored in the staging layer. Difference is very simple. Non-persistent staging layer, data is temporary, gets erased after use. Persistent staging layer, the data stays available even after processing. Naturally, the next question is, why would you choose one over another? A non-persistent staging layer has the advantage of saving storage space. Since the staging data is deleted after loading, you don't need to keep extra copies sitting around. And remember, end users never directly access the staging layer anyway. They only use the user access layer, but there are downsides too. Suppose your user access layer gets corrupted or accidentally deleted. If your staging layer is non-persistent, you cannot rebuild them because the data is already gone. You would have to go all the way back to the original source system and reload everything again. The same issue comes during the data quality checks. If you want to compare data warehouse with the data in the data warehouse with the original incoming data, there is nothing left in staging to compare against. So once again, you have to revisit the source system where the data is coming from. Persistent staging layer solves this problem very nicely. Since the original staged data is still available, you can rebuild the user layer directly from staging without reconnecting to every source system. It also makes auditing and data quality validation much easier because the raw historical data is still sitting there. Of course, this comes with trade-offs too. Persistent staging layer require significantly more storage space, especially when you are dealing with like millions or even billions of record. And there is also governance concern. If users of developers accidentally gain access to staging table, they might start using unprocessed or partially transformed data instead of the properly curated data from the user access layer. So in practice, the choice between the persistent and non-persistent staging layer usually comes down to factors like storage cost and recovery requirements and governance policies and how important those historical staging data is for the organization. In this video, we moved beyond the basic concepts and started looking at the actual architecture behind data warehousing. We explored different architectural approaches, including centralized setups and multiple decentralized models, and discuss the pros and cons that come with each one. We also talked about something closely related to data warehouses called as operational data stores or ODS, and understood how it fits into bigger data warehousing ecosystem. After that, we opened things up a bit and looked inside data warehouse itself, especially the staging layer. This is the part where huge amount of data from different sources first come in before being cleaned, integrated and restructured for data analytics and data-driven decision making. In the next video, we'll continue diving deeper into architecture, but this time we'll focus specifically on ETL, that is extraction, transformation and loading, and understand why it plays such an important role in data warehousing processes. So whenever you are ready, let us move on to the next video.